What? You and me will always be tight. Family every single day and night. Even when you start to acting like a fool.
Why do we need calculus? We don't.
We can model the shape of a blood vessel using a cylindrical tube. Due to the friction caused by the walls, the velocity of the blood is greatest along the central axis. It decreases as the radius increases and reaches the wall of the artery and becomes zero. The relationship between the velocity and the radius is given by the law of Laminer's flow, which is the velocity equals the pressure difference between the ends of the tube divided by 4 times the velocity of the blood times the length multiplied by the radius squared minus the radius from the central axis squared.
Okay, so what we just previously saw was that velocity of blood flow is calculated through this problem, in which we know that v is velocity. We know that lowercase r is the distance from the central axis. N is the viscosity of the blood flow. P is the pressure difference between the ends of the tube. L is length, and R is radius. So we can see here that velocity is equal to the pressure divided by 4 times the viscosity times the length, all multiplied by radius squared minus the distance from the central axis squared. By using the velocity equation that was previously stated, we can take the limit of that, which gives us the exact value of the flux, which is also known as the volume of the blood that passes through the blood vessel per unit time.
Okay, so we know that the flux is equal to the antiderivative of 2 times pi times the radius times the velocity with respect to r as 0 goes to the radius. From this, we can find Poiseuille's law, and we will have to take the antiderivative of 2 pi times the radius times the velocity, which we were given in the last part of the video, which is P over 4NL times R squared minus R squared, all to dr. From 0 to the radius. From here, we can pull out 2 pi times the pressure over 4NL, and when we simplify that, we will get pi times the pressure over 2n over the length. Once we pull this out, we will end up with the pi times p over 2NL, the antiderivative of big R squared times R minus R to the third dr from 0 to R. This will then give us pi times pressure 2NL, put it in brackets, R squared, which is a constant, and then we find the antiderivative of R, which is going to be R squared over 2, minus the antiderivative of R to the third, which is going to be R to the fourth, sorry about that, over 4, close bracket. The radius is R equals big R equals 0. This gives us pi times p over 2NL, R to the fourth, once we simplify it, over 2, minus R to the fourth over 4, which equals pi times the pressure times R to the fourth over 8 pi times the length. Once we plug in 0, if we plug in 0 into this equation right here, we will end up with 0. So once you take this minus, well, once you take 0 minus this, we will just end up with this equation right here, leaving us with that as our Poiseuille's law.
Yeah, turn up. Yeah. What?
An example of how we can use Poiseuille's law in medicine is by calculating the rate of flow in a small human artery by plugging these values into this function. So we know that F equals pi times pressure, which is 4,000 dynes per centimeter squared, times the radius, which is 0.008 centimeters, over 8 times the viscosity, which is 0.027, times the length, which is 2 centimeters. And when you enter that into the calculator, you will get 1.19 times 10 to the negative 4 centimeters cubed.